You may have looked at the electrostatic interaction energy in the previous video and said that looked pretty low. So we talked about that being 13 to 17 kilojoules per mole, which is much smaller than a covalent bond. Although you may remember from discussions in Gen Chem, for instance, that the ionic bond is the strongest bond, right? But when we're talking about that, we're talking about the crystal lattice energy for sodium chloride, okay? So that's when the sodium cation and the chloride anion are in crystalline form, okay? So it's something about the environment that the charged species are in a biological system versus in a crystal that changes this energy drastically by well over an order of magnitude, okay? So to see why this is, we're going to look at Coulomb's law, which allows us to calculate the interaction energy between two charged species. So this is the equation here, where E equals K times Q1 times Q2, and then in the denominator we have a term called epsilon and a term called R, all right? And we'll go through each of these terms right now. So E is the interaction energy, so that's, again, for instance, what we're calculating in these two instances. So it's the energy required to break the electrostatic interaction, right? K is a constant, so this is actually formulated by 1 over 4 pi epsilon naught, which is the permittivity constant. So we roll all of these in together to form one constant, and it's 9.0 times 10 to the ninth joules times meters per coulomb squared, okay? So the coulomb, note the coulomb is in the denominator if you write it out, for instance, like this. All right? Epsilon is the dielectric constant, so this changes depending on what environment we're looking at the electrostatic interaction in, and this has become really important. And then R is the distance between the two species. All right? So let's do a sample calculation that kind of looks at the crystal lattice energy, for instance, right? So let's say we have sodium cation and a chloride anion, all right, in a crystal lattice. So I'm not going to draw the whole crystal lattice, but we know we have these interactions between the two, all right? So our R is going to be between the center of mass for these two. All right, so that'll be R. And for this system, we're going to use the estimate of, hold on, 2.73 angstroms. Okay, and we're going to convert that. All right, 2.83, excuse me, 2.83 angstroms. Let's try that again. R equals 2.83 angstroms, okay? And that's equal to 2.83 times 10 to the negative 10th meters, all right? So that's our R value. The charge for this is going to be plus and minus 1, but we put that as the electric charge. So each charge, for instance, is going to be multiplied by the charge of the electron, which is, so for instance, Q1, if we call Q1 the sodium ion, is going to be 1.602 times 10 to the negative 19th coulombs. Q2, put that in blue, equals negative, which is the chloride anion, negative 1.602 times 10 to the negative 19th coulombs, okay? And in this system, we're going to take, for the crystal, we're going to take the dielectric, we're going to set the dielectric as 1, All right, and then are we missing anything? We have the radius, dielectric, we have the charges, and we have the constants, okay? So if we multiply this all out, you're going to get energy equals 9.0 times 10 to the 9th joules meters over Coulomb squared. All right, on the top, we're going to multiply Q1, Q2, so that's going to be 1.602 times 10 to the negative 19th squared. Is that still on the board? Nope. .602 times 10 to the negative 19th coulombs squared, all right? And then there's 1 plus and 1 minus, so plus 1 times minus 1 is negative, so this is going to have a negative value on the outside. And then our dielectric is 1, we're going to leave that there, and then our R is 2.83 times 10 to the negative 10th meters, okay? Now, this all calculates out to about 500 kilojoules per mole. Okay, negative 500 kilojoules per mole. Okay. Okay, what that indicates is that, one, we have a negative value, okay, so that interaction is favorable, right, for this energy. And then it's about the same as what we get for the crystal lattice energy when we calculate this out. So the crystal lattice energy is an experimental value, so we have a discrepancy between these two energies because there are other factors such as long-range interactions between the ions that help to strengthen this interaction that we're not taking into account in our very simple calculation here, okay? But this is our calculated energy. So if we look, though, now let's say we replace this, the sodium chloride interaction, instead of being in a crystal, which means it's mostly interacting with air and has this very low dielectric, if we change this interaction into water, all right, the dielectric also changes. And so we can think of R as remaining the same in water. Q1 and Q2 are going to remain the same. So the only thing that's going to change is the dielectric. So the dielectric for water, though, is 80. All right? So what that means is that this interaction is divided by 80 instead of divided by 1, according to this equation, right? And so when we do that, we get 50 divided by 80, or excuse me, negative 500 divided by 80. So negative 50 divided by 8, that's about 6 1/4. That is 6.25 kilojoules per mole. Okay, so then you can see how the water, just by changing the system from being a crystal into water, drastically changes the interaction energy between these two charged species. And so that's what we see, for instance, when we're looking at the electrostatic interactions, the typical electrostatic interactions in a biological system versus, for instance, the ionic bond of sodium chloride in a crystal lattice.